Good morning, dear students. Welcome to another session of DSP architecture and algorithms. So, in previous session, we were looking at different types of addressing aspects like indirect addressing, direct addressing, say offset addressing. Now, apart from that, we looked after another addressing mode that is called as circular addressing mode. So, in which three parameters what we have to look out for is SAR, that is start address register, and EAR end address register, and PNTR. So based on this, again we had some discussion. What happens if SAR is greater than EAR, and when PNTR is updated, what happens if it goes beyond this one or beyond this? So what is the case? And the same thing when SAR is lesser than EAR and when SAR is greater than EAR. So these were the different conditions what we had checked out and how the update has to be done. And we saw that the buffer size is SAR minus difference between SAR and EAR plus 1 to that. Now if I just take an example, suppose you have these four uh, locations, for example. So this is 100. So let me call this as SAR, and AAR as per this one would be this is 101, 102, and 103. So what is the buffer size? Buffer size is 4. That is 1, 2, 3, 4. So if you take the difference between these two, that is say AAR difference SAR, it turns out to be 103 minus 100. So which is 3. But actually what is the buffer size? That is 4. So therefore the buffer size is difference between these two plus 1. So difference between AR and SAR plus 1, which is 4. So this is with respect to circular addressing. So, and with respect to that, we saw that when we update the pointer, what are the different conditions possible? Either the pointer moves beyond AR or it moves beyond SAR. And that pointer has to be updated based on if whether SAR is greater than EAR or whether SAR is less than EAR. And apart from this, I mentioned why this condition comes, because sometimes addressing might be like this: 100, 101, 102, 103, or sometimes you might go in the reverse order. That is, here it might be 100, then 101, 102, 103. So you can see that in this one, SAR is lesser than EAR. If addressing is in this form, EAR is greater than EAR is less than SAR. So based on these conditions, you should be updating the pointer in the circular addressing mode. Now another one addressing mode is the bit reversed addressing mode. So yesterday we started with the discussion of this. So what is meant by bit reversed addressing? So in simple, in your binary form, if two bits are used, so 00, 01, 10, and 11. Say, for example, you have a sequence x of n, and you have some samples associated with this. Say, for example, I have 4 samples. So this sample's index is 0. So in your binary, it will be 00. The index of this one is 1. So in binary, it is 01. Similarly, index of this one is 2, which is 10, and the index of this one is 3, which is 11. So these are the possible, these are the indexes which are related to say x of n. Now in bit reverse, what we do, because in FFT, when we apply FFT, generally the outputs are in bit reversed form. Either the outputs you place in bit reverse form or the inputs you place in bit reverse form. But now what happens is, so these samples will be sitting in over here. Say for example, x of 0 will be here, x of 1, then x of 2, and x of 3. That is 1, 2, 1, 1. The values are 1, 2, 1, 1. So they'll be sitting in the memory location in this form. And when you're doing when you are operating in bit reverse form, what happens is these sequence numbers which are in binary. Instead of writing it in this form, you'll be writing it in the reverse form. So that is first the ls bit and last will be the ms bit. So this will be 00. So this is your in decimal it is 0. Similarly, this one, first you write the ls bit and then you continue in this direction and then you write the ls bit. So this is what in a decimal it is 2. So similarly, this also. So this is 1 and this one is 1 1, which is 3. So this is bit reversed address. This is bit reversed address. It implies that the first sample is at this location, next sample is at this location, next sample is at this location, and the next sample is at this location. So this is how bit reversed addressing operates. So if you remember, you write the butterfly diagram, remember all these things. So you draw the butterfly diagram and then you try to give the inputs, and here you'll be getting the outputs. So if they are given in proper form here, that is without bit reversed. Here they'll be in bit reversed form. Here they'll be in bit reversed form. So we should take down the samples in proper. So this is one special case with respect to your DSP. Now, how do I actually go ahead with accessing these addresses? Now, I cannot have, say, if there are 16 bits utilized for addressing, if there are 16 bits present in this, so that is 000, there are 16 bits. Now, imagine whether I can go in taking reverse operation every this thing. So I have to take the ls bit, I place it in the next, then next. So this becomes a tedious process and it is a time consuming process. So which is not intended in your DSP. So how do I go ahead with such kind of aspect? So there is one simple technique what they follow in order to achieve this bit reversed addressing. So I do not put it as, so if 16 bits are there, I do not take bit by bit and then perform the operation. Obtain the address and then go and store the information or access the data which is present at the location. So this we are not doing because it is time consuming. So instead of that, we have a different technique. So that technique is here. So we see what is the current index. In order to get the current index, we use the previous index plus the half the size of the FFT, half the size of the FFT. So let us look at this one with an example. So whether we are able to achieve this bit reversed addressing. So now here we can see that in this example, what we have, compute the sequence in which the input data should be ordered in 16-point DFT. So what is the size of the DFT? Size of the DFT is 16, 16. Now, so what is half of that FFT size? It is 16 divided by 2. So which is 8. That is B of this part is equal to 8. Now I want to compute the sequence in which the input data should be ordered. So it is indirectly for DIT FFT. So input sequence should be ordered in bit reversed order, bit reversed form. So in order to compute that value, right, what we do, so we assume that the first address of the sample is 0. First address of the sample is 0. So it is like the index. So we spoke about 00011011. It's a bit reversed is this case. So it is 0th this thing. So if first this thing is 0, what should be the value of the next address? Now here I have just taken 2 bits, so it is like 4 samples. Now you have to take 16. So it is 16-point DFT. 16-point DFT. Okay, if it is 16 point, then I require say 4 bits. I require 4 bits. So if it is 4 bits, then as per our logic, what we have. So first address is 00. Its bit reversed is also 00. So this is in decimal 0. Now next one is 0001. So if I reverse it, what should be the number? It should be 1000, which is 8 in our case. So whether next this thing I'll be getting this value. That is what I have to check out. So if I assume that the first address is 0, then as per this rule, if I have to identify the new index, then that is the next index or the current index, I have to consider the previous index and add it to the half the FFT size. Half the FFT size. So here we can see that previous index was 0. That is because we had assumed it to be 0. 0 plus half of this value, that is 0 plus 8, which is equal to 8. So in your decimal form, what is the value? It is 8, and in its binary form, it is 1000. So this is the next address of the sequence. This is the next address of the sequence. Now here one special thing comes over here. So if I just try to estimate what is the next value. So here it is 0100. It is actually 4 in our case. It is 4 in our case. So I should get this value. I should get this value. So now the new index is what? New index is, the current index is 8. Now I have to estimate the new index. So first one was 0, next one was 8. What is the next index? What is the next index? So in order to do that, so again, what I do, so as per this one, I take 8 plus half the size of the FFT. Half the size of the FFT. So in this case, one second. It is like 8 plus 8. So this turns out to be 16. But this is not the way how we add in bit reversed addressing. So just a minor change in this case. So how do I go ahead with the addition? So what is 8 in binary? 8 in binary is 100. And what is this value? That is 8. So first one 8 is here. Next one I got that. Next is also 8. So this is also in binary. So when I add, it will be actually 16. So here we are not following your regular addition method. So what we do is, this is 8 and this is 8. Now we add it. So in your regular addition, what you do, you start from LS bit and you move in this direction. But for bit reversed addressing, what you do is you change this direction. You start from MS bit and move in the other direction. So what is happening is carry moves from MS bit to the LS bit. So this is one of the major difference what we have to look out for. So therefore it is termed as a reverse carry add operation. So this addition what is there, right? It is actually performing a reverse carry add operation. So here what we have, so if you just observe 1 1, what is the result? What is the sum of this? Sum of this is 0. Now we have a carry generated from this. So this carry should be sent to the next this thing. So carry comes over here. So it is 1 plus 0. It is 1. There is no carry. 0 plus 0 is 0. 0 plus 0 is 0. So now I am getting 4. So remember, you in bit reverse addressing, you start with MS bit. You propagate the carry in the reverse direction as with respect to your regular addition what you do. So then I'll be getting this value. Okay. So we are discussing about the speed issues. So with respect to speed issues, what we have, uh, in a microcontroller, speed is not a major concern, but in a DSP processor, speed is a major concern. So you try to execute the instructions or perform a certain task at a very high speed. That is, you try to achieve the results as quickly as possible or perform the operations as quickly as possible. So for these purposes, that is to overcome the problems which are being faced by the microcontroller, we look into different aspects. So the first thing which comes is the hardware architecture. So with respect to this, previously we had discussed so many things. That is, we discussed regarding the shifters. So how we can attain shifting operation in just one machine cycle. How we can attain say multiplication result in just say single machine cycle. So we discussed regarding barrel shifter, which helped us perform shifting the say shifting of n number of bits in just one go. Similarly, Brown multiplier. So Brown multiplier also helped us to identify that in one go I can obtain the result of the multiplication instead of waiting for the entire operation to be performed in say as it is performed in your say microcontroller, in which microcontroller basically use overlap and add method, or overlap and add method, shift and add method. It uses shift and add method, but that is not done in your DSP architecture. So for that, you go ahead with the Brown multiplier. So we had seen these all things. Then apart from that, we saw that we have uh, say on-chip memories. So why on-chip memories? On-chip memories are fast to access. If you provide the memory outside the processor, then you should provide interface to that. You should provide interface to that. So if you're providing interface to that, then what happens is you have to again access the bus, go to the memory, fetch the data, and come back. So this will consume a lot of time. So instead of that, if I provide a on-chip memory to the DSP, the access will be faster enough, and the operation can be performed at a very high speed. Similarly, other kind of hardwares are also utilized. That is, say the hardware architecture. One specialized this thing is the Harvard architecture. So in Harvard architecture, what do you have? You have separate memory for a program and separate memory for data. So if you just remember in two separate memories, so at single time only we can access say the instruction, then we can access the operands. So if you have again say two operands have to be accessed, you can provide again more so more than one memory, more than one memory for data and one memory for program. So that is we just observe. So it all started from this point. So that is the first point, the Braun multiplier. So this is a specialized hardware architecture which helps us increase the multiplication operation to achieve the multiplication operation at a very faster rate as compared to your shift and add method which is utilized in your microcontrollers. So then we discussed regarding what should be the buses available, what should be the size of these buses, whether I can provide separate buses for each. So we had discussed all these things. Again, we discussed regarding shifter. So we discussed regarding the barrel shifter. So here in this, in one go itself, we'll be able to shift say as many bits as possible. Whereas in your regular microcontroller, if three shifts are required, three shifts have to be done, then you have to go, for example, you might require three machine cycles. But for the three shifts in your barrel shifter, will require just one machine cycle. So then apart from that, we had multiply and accumulate unit, which is performing operations at a very faster rate. So this kind of things are present because you have operations which require multiplication and addition to be performed. So for example, in your convolution, you require that. So if I go for your regular operation, it might take very long time. So example we had taken over here, which requires 25.7 microseconds for 256 products. But if I go with the regular microcontroller, it may be in terms of seconds, not even in microseconds. So that is a very huge difference when comparatively. Then apart from this, the other hardwares what we looked out was the ALU. So ALU should be consisting of all these things. Then we had the bus architecture and the memory. So here we have the von Neumann architecture, which is basically present in your microcontroller, but this is not visible in the sense it actually hinders the speed when we use it in the DSP. So therefore, what we do is we go for Harvard architecture where we have separate memory for each program and data. So what does this do is this actually helps us improve the execution related to DSP. So here is another, still if you want to still improve it further, what you can do is you can provide one memory for program, one memory for data and another memory for data. So two operands are required. So fetch it at one go and then perform the operation. So this is still improving the speed with which the DSP processor implements the operation. So these are, and then we had discussed regarding on-chip memory. So if we provide on-chip memory, what is the advantage? So these are the things with respect to which the speed issues are overcome in DSP. Overcome in DSP. That is with the use of the hardware architecture. So then apart from that, we have parallelism. That is, if I'm able to perform multiple operations at one go, then it will be feasible enough. So this question comes because in Mac unit, if you just observe, so two operands are given, they are multiplied and then given to adder, and by that time the next one comes in. Say in this case, what happens is if there is only one, say ALU, if there is only one ALU has to perform your addition, multiplication, and fetching of the addresses, because even addresses also have to be added, decremented, subtracted. So there also mathematical operations are involved, and we saw even in bit reversed or circular, we have to perform those mathematical operations. So now imagine if Mac unit is having its own ALU, that is one specific ALU which performs only operations with respect to the data, and there is another ALU, and there is another arithmetic unit which is dedicated only to calculation of the addresses of the operands. So in such cases, what happens is the execution speed can be improved. The execution speed can be improved. So that is, say if I'm just taking, so if I'm just taking over here, right? So what is happening? Two say operands are coming in. You are calculating the result and then you're storing it. By that time, the next instruction should be available. The next operand should be available. So in performing this, what happens is, say you're adding and subtraction. So this is being performed by your arithmetic and logic unit. Now what happens is, in order to calculate the address of the next operand, also you should perform some mathematical operations. So again, you might add or subtract. So if they're stored in one sequence, you should keep on adding the address of the previous operand and then keep on fetching them. So this also should go to the ALU. Now what happens is ALU is kept busy over here. Now what I do is if I separate this ALU, if I separate this ALU and it performs only the operation related to these operands, and the address calculation is done with another arithmetic unit which estimates the addresses. So if I do this, then it will be pretty helpful. So what happens is, if two separate this thing is there, one this thing is performing the say address estimation, and the other one is performing the addition or subtraction of the results. So in this case, what happens is, in parallel you are doing two things. You are performing your mathematical operations on the data over here, and you are performing the mathematical operations to fetch the operands over here. So it is like parallel this thing what you have, parallel operations. So this definitely increases the speed of execution. Then apart from this, you can observe that here what is happening is, when x and y are being multiplied, you are getting access to the next operands. You are getting access to the next operands. So when you're multiplying x and y, you're getting access to the next operands over here. So by the time the result goes here, that is multiplier result comes to the add and subtract, the next two operands which are present over here will be given to multiplier and its result will be available. So in this way, what you're doing is you are pipelining the entire stuff. You're pipelining the entire stuff. So this also actually improves the speed with which the DSP executes. So parallelism and pipelining are basically achieved with this case in order to improve the speed with which the execution goes around. So this is what we are doing. So just an example they have specified instruction one is being executed, that is two operands say x and y are being multiplied. So that result is available in the next step. So by that time your multiplier is free. So you get the next this thing, next two operands, you perform the result, and by that time this result is being performed, say addition is performed and it goes to the next step. So this continues. So once the entire pipeline is filled, then your execution goes in a smooth way and it will consume less amount of time. So this is what is happening with respect to increasing the speed with which the operations are being performed. Now, apart from that, system level pipelining, if you just observe, say this equation, what we have, it is actually convolution of these two. So this is actually, say, I would specify it as circular convolution, which is having 8-bit sequence. So you can see that h of I into x of n minus I. So it is h of 0, h of 1, h of 2 up to h of 7. Here x of n minus 0, n minus 1, n minus 2. So if I have to calculate the first y of 0, then substitute n is equal to 0 in this equation, you'll get the first value. Then put n is equal to 1, you'll get the next equation. So can I implement the same thing, since it is multiply and accumulate kind of operation, can I do it in the Mac unit? So wherein I'll be having the pipelining and parallelism implemented. So that is what they have specified here. So here what you have is you have two multiplexes which are being used and they are given to the Mac unit, and it will be providing you result in a parallel form. So here you can see that these all things are applied in parallel. And when we are using the Mac unit, we also saw that pipelining also comes into play. The Mac unit itself is implementing the parallelism and pipelining aspect. So this is just an example with respect to the convolution of the two things. Okay. So that is what we have over here. Okay. So here again we have pipeline implementation for the FIR filter. Okay. So this is again dependent on the previous equations what we had discussed. So this again improves the speed with which the DSP executes. But what is the problem with these things is again it increases the cost. So the same things is specified over here. Now the last one what we have to discuss is what are the features of external interfacing. Now, in a microcontroller also, you have to deal with external devices. See, I want to connect to a LED. I want to connect to a, say, GPS module. I want to connect it to a GSM module. So, if I have to do such kind of operations, then I should have interfacing aspects. So, similar kind of interfacing aspects should be made available to the DSP devices. Should be made available to the DSP devices. So that is what it looks out for DSP. So it should provide the features in order to make external interfacing available.